out of it. Not very. It's nice from a decision standpoint because you can truncate that constellation, but obviously that's not the best use of energy. There's another type of constellation that's better for 3 that I'm going to get to momentarily, so I'm going to leave that to the side. So 1 is trivial, 3 is ugly, and then when we get to 5 and beyond, we get to what are called the QAM cross constellations. And these are kind of interesting constellations to look at. So for B greater than or equal to 5 and odd, the QAM cross is actually better than the QAM square for odd numbers. Let me show you the first one. And in order to do that, to draw this thing easily, I start with a 16 square in the middle. 16 is not enough points. You need an additional 16 points. So we put them in the 4 positions of lowest energy on each of the sides of the constellation like this. And what happens is you get a constellation that kind of looks like the International Red Cross symbol. And that's where the name comes from. A lot of these standards for early modem transmission, in fact, for almost everything these days in telecom, get decided in Geneva. And so I have a feeling when there was even a standard called the V.32 modem, which had 32 points in the constellation. And they skipped a bunch of numbers just so they could call it V.32 because it had 32 points in the constellation. Uses this particular transmission symbol constellation. The cross, that's where the 32 points are. Now what happens is when you go to larger QAM crosses, each time you add another couple of bits, like to go to 7, you take each one of these dots and put 4 dots there. And that's how you get the next largest size cross constellation. And you'd have 128 cross. Instead of having a hole of just 1 point in each of the corners, you'd have a hole of 4 points. Next one after that is 512 cross. Okay, and you'd have 16 points where each of these are. And these are how the cross constellations are actually generated. Let me, another way to look at this is the 32 cross is a 6 by 6 square with 4 corners deleted. Or 128 cross would be a 12 by 12 with 4 4-point corners deleted. This is a 4 here. And I could go to the 512 would actually be a 24 by 24 with 4 16-point corners deleted, so forth. So you could draw them in these various ways. Okay, now for this constellation, you can see with just the corners missing, but otherwise forming this grid, where again the distance between points is going to be d, it's possible pretty easily to decode the points. Essentially, it's truncation again. If you get out here in one of the corners and you get a point when you truncate that's not allowed in the constellation, well, then you can do something special to actually pick the closest point within the set of allowed points. If we again work the nearest neighbor union bound, what happens is we get, again, not quite an equality, but a tight bound. Obviously, most of the points in that constellation have 4 nearest neighbors, except for a few on the outer boundaries. And if you work through that, this fraction of points turns out to be 1 over square root of 2 times m, or m is 32 or 128 or 512. That's your nearest neighbor count. And we get q of almost the same formula we saw earlier. We're going to have a 3 up in the numerator again, just like for square QAM and for PAM. But down here in the denominator, what happens is we get 31 over 32 times m minus 1. So instead of just getting m minus 1 like we had earlier, we get this little multiplier 31 over 32. And actually, if you look at that, that's a smaller number in the denominator. So the cross constellations are a little bit better than the square constellations in terms of their use of signal-to-noise ratio. Not enormously so. just this tiny little tenth of a dB or so here, this factor of 31 over 32. Why is that true? Well, we're using the energy a little better by deleting corner points here. The square actually includes the corner points. The best thing to have in 2 dimensions would be to have all your points within some circle. That may not be the cross constellation, certainly not the square constellation. It gets harder to implement to try to keep everything, because then you got to keep track of all the points that are allowed within the circle or not allowed when you're making decisions in the receiver. And is it really worth that much to you to be able to do that? For QAM, it's not worth much. You get maybe an extra tenth of a dB plus what you're getting here to do that, and it's a lot of extra complexity in the receiver for not too much gain in the design of the system. But that's where that little 31 over 32 is coming from. It's closer to a circle than the square constellation itself. But otherwise, the formula looks pretty similar in terms of PAM and QAM. Now, I promised that I would come back. In fact, you have this problem on your homework next week that you'll see. It's kind of a neat problem. There's an alternate odd constellation, which I sometimes call the odd square. And what happens is, in order to get any odd constellation, you take the number of bits and increase it by 1, double the number of points in the constellation. So for instance, for 3 bits, I would put 16 points in a square constellation. That's why I call this a square. And we take every other point. So there they are. Okay, so this is every other point from the next largest square, and this would be called the 8 square constellation. And this is probably the one that's most heavily used for 3-bit transmission. You could do this for 32 square, and it would be every other point from a 64 QAM square. And what you'll find in the homework problem is that all the energy, distance relations are the same as the square. Basically, you use twice as much energy, but you get twice as much distance between the points. You can see that the distance here is increased by square root of 2. So you're going to get the same formula for the probability of error. The number of nearest neighbors is going to be slightly different as you go through. You can see on the edges that changes a little bit from the square constellation. But basically, the outside of that minor difference in nearest neighbors, it's the same. And it's a lot easier to design. It's not as good because you don't get this 31 over 32 in the denominator. So you lose about a tenth of a dB. You're just going to get this m in the denominator for the odd square constellations. Okay, let's look at the relationships here of either 3 times SNR over 31 over 32 times m minus 1, or for the square constellations, m minus 1. What happens is every time I increase the number of bits transmitted by 1, basically I square m. If I were to stick in here 2 to the b, if I increase the number of bits by 1, then I have doubled the denominator almost. When m gets big, I can ignore this minus 1. So what happens is with twice as much in the denominator, same signal-to-noise ratio, the cost is 3 dB, that's a factor of 2, per bit in QAM. All right, so that's kind of classic result. Remember, adding 1 bit in QAM is kind of like adding a half a bit per dimension. In order to get 1 bit of per dimension in QAM, I have to actually add 2 bits because I divide the number of bits by the number of dimensions, which is 2. So the 6 dB per bit we saw in PAM was really 6 dB per bit per dimension. And in QAM, it's only a half a bit per dimension when I add another bit to the constellation. So there really is the same rule of 6 dB per bit per dimension. But in QAM, the most commonly heard rule in communications is it costs you 3 dB per bit. That rule tacitly assumes two-dimensional modulation like QAM is being used, and you must have another 3 dB of signal-to-noise ratio to increase the number of points in a QAM constellation by 1 bit's worth, or essentially 1 bit's worth is doubling the number of points in the constellation for transmission. So 3 dB per bit is the rule, and we could go ahead and create another table and work out for various signal-to-noise ratios. From that table, how many bits per dimension I could transmit, or how many bits per symbol I could transmit. We would expect 13.5 dB for the 4-point constellation, and then we know we'd need 3 dB per each additional bit beyond the 4-point constellation. So 16.5 dB to get 10 to the minus 6 error rate with the 8 square, and then about 20 dB or so to be able to get the 16 square constellation and so forth in transmission. So we're going to try to get your intuition going well. If you got the signal-to-noise ratio, you kind of know what to do in terms of how many bits per dimension. You can begin to design the rest of the system for any type of transmission system. So I'll harp on that a bit to try to build your intuition, because I find as an engineer that's working in transmission that this is one of the most commonly encountered questions is, well, how fast do you think we can go on this channel? And the second question, after you tell them the answer to that, the second question, well, how much is it going to cost to do that? And you can build a good intuition just by kind of having a few signal-to-noise ratios in your mind and knowing that PAM, QAM follow very similar patterns. You can begin to say, oh, well, that would be about 10 megabits per second on this channel. We can investigate more of the details of that and get into an exact implementation if you'd like to go further. But this is roughly what you could do on this channel. So it kind of gives you a good intuition as to whether you should pursue anything any further. We're going to come back to the gap approximation in Thursday's lecture, and we'll let you go for now, and we'll see you again on Thursday.